Okay, so far we have covered data, BSS, stack, and text. Now there is one small section left, which we wanted to just go over for the sake of completeness, and that would be the heap. Now, before we sort of deep dive into what heap is and why it is needed, uh, we'll also talk about the motivation behind heap as to why it is even there. And secondly, the full disclaimer that for the embedded systems, I have hardly seen heap being used anywhere. And the reason is very simple, because with heap and with dynamic memory allocation uh, comes a sort of unpredictability, I should say, for the lack of the better word. And the unpredictability comes from the standpoint that we don't know when the heap will get exhausted, when our code will run into low memory, or memory not available, and it can cause some
Hmm.
adverse effects. Now
Hmm.
think of your washing machine or your microwave or any other embedded system which is there to do just a particular task, and if
Then
it runs out of.
how about engine firing system?
Oh, wow. Automobiles, right? Yeah, why
Yeah.
not? Yeah.
Or the
So
X-ray machines.
X-ray machines, yeah. Think of them being running out of memory and running into some, hey, I can't do anything. I'm out
Hmm.
of memory. I'm gonna, keep the state to where it was when I ran into this problem. So X-ray machine could keep on firing. Automobile can maybe, just absolute braking system. Like it could just engage
Brake,
brakes and yeah,
or
or
it could just go haywire and be
haywire
like, I'll fire the engine even
engine
more.
more. Yeah.
I mean, we don't know what
We don't know.
happens.
So,
Catastrophes can.
right, are limitless, and precisely for that, we don't want any uncertainty in our code. If it can be
Yes.
introduced by some concepts, some libraries, we are willing to remove them altogether and never use
Yes.
them. Okay.
And in
So,
fact, we want our code to be as
predict
predictable
as possible. Yeah.
and whatever. I can't spell while I talk, but
Deterministic. Yes.
yeah. So something's
Hmm.
happening. System here
Hmm.
keeps on switching between. Anyways, go
Hmm.
ahead.
All right. So now, having said that, and this could be another query which could be asked, that why do we not use heap and dynamic memory allocation in the embedded system? And the answers are pretty much what we discussed. All right. Now moving to the motivations. Like, having said that, heaps are not that bad. Okay, they are there for a reason, and
Yeah.
the pros which they bring to the table are I think are unsurmountable. So let's say you are, I mean, for a very crude example, we all must have in our college, whenever we took the C course, would have designed this program where we add, like, marks of some students, right?
Yeah.
Where we have, like, hey, input the student's record, and then we'll,
Yeah.
like,
Yeah. Yeah.
add up the marks and display out the results. We most likely would have done this exercise or a very similar one to this,
Hmm.
right?
Hmm.
Now, there, if you remember, we had already always assumed that there cannot be more than 100 students or some number,
Right.
right?
Some number, yes.
Yeah, and again, we want to introduce predictability in our code, that hey, I can handle up to 100 students. But think of, the real world systems out there. There are ERP systems which are doing that,
Hmm.
and if they were written in C, you want your code to be as extensible as possible. Sometimes the numbers can increase and code can go beyond 100.
Correct.
In that sense, what the problem is, that why can't we not arbitrarily have any number, is because of the limited storage space. So if you can
Hmm.
say, hey, allocate an array, or allocate a structure, array of structures of, some 10 million or a billion entries, you are basically wasting 4 billion bytes right then and there.
Right.
So we wouldn't want
Pretty
that.
correct. So that's a good point. That
Hmm.
if we are working with fixed memory, the statically allocated memory. So
Hmm.
what that means, by the way, is you have int, let's say mem, and you just have an array, actually a character array, let's say.
Hmm.
So this is like static allocation. Upfront, you say in the data section, this is a global. So in the data section, I need a variable called mem, and I need 1024 bytes. So now 1024 bytes are reserved, and in an embedded systems, typically we'll use this approach because
Right.
again we want to control the space on our own. We have like a tight bound.
Mm.
But what Mohammed was hinting at is, let's say you wanted, instead of 1 KB here, what if you wanted 1 MB? Then that much space within the data section for an embedded device is again all of a sudden a problem. That is number one. But what if you want now in GBs? So this approach is like clearly out the window. And
Right.
when we are talking about the GB scenario, we are no longer talking about embedded systems. Let's abandon those.
Yeah.
Let's talk about the hosted environment. So let's say your C code is actually a database management engine, right, where it kind of reads the file, collects the data, saves it in the memory. So how is it supposed to save it in the memory? Or it collects data from the users and then saves it in the memory. So what needs to happen is, for the new data that's coming in, the C program has to all of a sudden kind of ask for more memory to save that incoming values. So the way that is done is by having this notion of heap. Correct, Mohammed? Is that reasoning correct?
Yeah.
No. So the precondition then is, what you should imagine is, there is data coming in that needs to be saved. And that data is not like tiny amount of data,
Right.
not small amount of data. Not
And
in
plus,
KB.
we don't know the size of the data which our
As
program
well.
would encounter
Yeah.
in the beginning. So
Correct.
if your program is run once, in some cases it might require just an MB. In some other cases, it might require some few hundred MBs, and in some adverse cases, it might even run to GBs. But that is not known. The behavior is not known.
No, right. And we don't have like an upper bound on the data per se.
Right.
A good example would be, let's say, in the kernel, the Linux kernel, for example, how many processes can be added? There's no limit on it. The kernel doesn't come with a disclaimer saying, hey, more than 100 processes and I cannot handle it. What it will do is, if it doesn't have memory, it will crash. But it will let you add more and more processes. So what is happening there is, it is dynamically allocating a chunk of memory for each new process that comes in from its own heap or the RAM essentially. But the idea of heap is that you don't know what the upper bound on the data is. You're okay failing in case you cannot handle the incoming data. And that's about it. So yeah, go ahead, Mohammed.
Yeah. Okay. So you have a heap, which is basically a segment in your memory devised particularly for this dynamic memory allocations. And now you have, along with that, some management or some algorithms which are called heap management algos, which your standard C library also provides. So they are like DL malloc. Then people have written all sorts of crazy efficient code which manages your heap. And the reason why they are called heap was, initially they were being handled by this heap data structure, min heap or max heap. Now that might not be the case here. People have they have now different, I don't want to go into the detail, but there are very complex data structures now to handle or manage the heap. But initially they were being done by that. So you have like these APIs provided by these management functions, which are again wrapped by this standard wrapper, which we know for and know and use, which are called malloc, calloc free, which internally call this management heap management functions algorithms to manage the heap for us. So we can arbitrarily demand any a chunk of bytes from the heap, saying, hey, I need these many bytes, please provide me a pointer for it. So malloc will do that for you. And once you are done with the processing and your storage, and you want to return it back, you call the free. So ultimately what's happening is your heap section in your RAM is being utilized to allocate memories from there. Okay.
And so what I want to then do is, also one thing people need to remember is, you can ask any amount of memory using the malloc. If it cannot allocate that memory, if the algorithms cannot allocate that demanded memory, it will usually return back a null pointer, or it will fail. That is the idea. It will attempt, But if it doesn't have the memory to be allocated, it will just fail. That said, what I now want to do is draw this picture again and kind of point out where the heap resides. So in the ROM, we said there was .data section, the load address, using the load address. Then we said there would be .text section. Somewhere in passing, we talked about the .ro data section. If that exists, well, it will go either as part of the text section or a separate section, but reside in the ROM. The load address is of ROM, and the logical address, meaning the address to access the variable, will also be of the ROM in case of RO data.
RO data. And in case of freestanding, basically. So here we are talking about the freestanding environment.
Correct. Freestanding environment. In fact, by ROM, I then mean read-only memory can be guarded by the operating system.
Right.
Hence, can live in the DRAM but be guarded by the operating system to be read-only.
Right.
The idea is the RO data is treated like read-only data, usually in the parts where only reads can be done, no modification. Then we talked that in the RAM, the data section is copied over. These are called the logical addresses. Then we also said that the BSS section is allocated here and zeroed out by some initialization code. The same initialization code also copies. I got disconnected. Oh, again. So the same initialization code also copies over from ROM to RAM, the data section. Then we said somewhere at the bottom there was like a stack pointer that goes upwards, and the stack is available here in the RAM. And now the heap is essentially here on the top. And who keeps track of freeing different chunks and allocating different chunks? Well, the heap management algorithms, the malloc, the free, all of that, they are aware. They are actually made aware. In case of an operating system, the loader will, or the operating system will ensure or provide those parameters of hey, heap starts here, it ends here, manage the memory in between. In case of the freestanding, again, the initialization code is the one which needs to figure out as to where does the heap start and heap end, and provide that the local heap management library. FreeRTOS, for example, has heap management. So the initialization code needs to give it those parameters of start and end. And also one final question as to who tells where the stack starts, who tells where the heap starts and ends, who tells where the BSS starts and ends. How do we figure all of that out? Well, in case of a freestanding program or freestanding the bare metal software firmware, that is kind of encoded in the linked script. So it's the initialization code and the parameters from the linked script that work together. And in case of an OS environment, it's usually the loader. It's usually the operating system which defines these parameters for your program. All right. So anything else to be added to this moment?
No, I don't think so. Just a small recap is heap is a no-no for an embedded system typically, just because of the unpredictability and undeterminism which it brings to the table. But having said that, on a hosted environment, on servers, which run massive, which runs and manages massive resources, massive amount of resources, heap and dynamic memory allocation is a must, and that is where the C provides this glibc wrapper to manage and control heap along with the heap memory management algorithms. So that's to recap everything we discussed.
True. Perfect. So I think with this, we come to the end of discussion on the
memory
allocation, memory layout. And what we can do now is, well, as part of next lecture, what we can do is we can jump onto some hands-on proofs for all of that we have talked.
Right.
So I suppose this is a natural end to this lecture. So what we'll do is stop recording here and catch you in the next one.